Hello everyone, welcome to the next chapter. In this chapter, let's talk about the shapes of molecules. So in this lecture, we'll talk about how to depict molecules with ions and how to depict molecules ions with Lewis structure, Valence-Shell electron-pair repulsion theory, and the molecular shape and molecular polarity. So let's start with the first one. How do you convert a molecular formula into a Lewis structure? So we use the following steps. First, we take the molecular formula and we place the atom with the lowest electronegativity in the center, and we start adding the A group numbers across all of the elements by placing the atoms. So add all the A group numbers and you can calculate the sum of valence electrons. From the sum of valence electrons, you can draw single bonds first and subtract 2 electrons from each of the bond. So then you will have the remaining valency, and then give each atom 8 electrons and 2 electrons for hydrogen, which gives you the final Lewis structure. Now, if the atom does not have, if this is the common process for single bonded atoms, when you have multi-bonded atoms, for example, where the central atom lacks octet, then we move the lone electron pair to make the bonding electron pair, so which makes it into multiple bonds. So we'll take an example of this and see how it works. So let's say we want to draw the structure for NF3. So when you compare between N and F, so N and F, N is the one that has the lowest electronegativity, and we are placing F on 3 ends. So the first thing that we want to know is what are the valencies. So nitrogen is a group 5 element, so the total valency is 5, and fluorine, there are 3 of them, and the fluorine group number is 7, so it becomes 3 times 7. So you have 5, 3 times 7 is 21. You have a total of 26 electrons in total. So from 26 electrons, we'll draw one bond each. So 1, 2, and 3. So from that we have minus 6 electrons. So notice that each bond is 2 electrons. So minus 6 electrons becomes 20 electrons left. Now start arranging each atom, each outer atom with 8 electrons. So notice that fluorine here already has 2. So 4, 6, and 8. 4, 6, and 8. Notice that you have a total of 20 left. So which means that now we have utilized 1, 2, 3, 4, 5, 6 pairs. So that's 12. You have 13, 14, 15, 16, 17, 18. Now we have filled everything in the outer circle. Now go to the inner part. Nitrogen here has 1 electron pair, because notice that it already had 6 electrons. It just needed 2 electrons to become octet. So this here is the Lewis structure for nitrogen trifluoride. So this is how we can draw the Lewis structure for nitrogen trifluoride. So use the same principle now and try for CCl2, CCl2F2, and PCl minus. So CCl2F2 and PCl2 minus. So I'm not going to do CCl2, you can try that on your own. Let me do PCl2. So you have phosphorus and chlorine. Chlorine is much more electronegative than phosphorus, so you have chlorine on each side. Now, so for this here, how many are the valency here? For phosphorus, so phosphorus is a group 5 element. So it's a group 5A group element, so 5 electrons. And chlorine is a group 7 element, so 7 electrons. And 2 times 7, so 5 plus 14 becomes 19, plus it also has a negative charge, which means that there's 1 extra electron. So there's a total of 20 electrons now. So we have 1 and 2, so that is done. Next, so from that we have left 16 electrons. So 1, 2, 3, 4, 5, 6, 7, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that gives you a total of 16 electrons. Here, this is where the PCl2 minus comes in. So this is how we can know that the structure here has excess electrons. So we can say, we can put it as a bracket and write the negative charge. So it means that there is an excess electron inside the original structure. So this is how we write the structure for PCl2 minus. So this is when you have an extra charge. Now, if there is a positive charge, which means that subtract 1 electron. If there is a negative charge, add 1 electron. So this is how we can draw the structure. So let's try the same for CH4O. So here carbon is the one that has the least electronegativity. So let's arrange the hydrogens first. So here they are talking about methanol. So methanol here is CH3OH, so oxygen, hydrogen. So we have arranged the atoms now. So let's draw the bonds later. Now let's draw the bonds. So 1, 2, 3, 4 and 5. Before we draw the bonds, we need to know how many valence electrons are there. So carbon is group 6, so 6 electrons, sorry, group 4, 4 electrons, and hydrogen is group 1, so 1 electron, and there are 4 of them, so it becomes 1 times 4, and oxygen is group 6, so we have group 6, a total of 6. So 4 plus 4 plus 6, that gives you a total of 14 electrons. So from that we have 1, 2, 3, 4, 5 bonds. So 5 bonds is 10 electrons. So minus 10 electrons becomes 4 electrons. So we have 4 electrons left to write down the structure. Now here notice that hydrogen needs 2 electrons to become valence. So balanced, so hydrogen, 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 so all of them have 2 electrons each. Carbon has 8 electrons in terms of the bonds. So the only thing that is unbalanced here is the oxygen, so we can write those 4 electrons on the oxygen, giving it the final octet structure. So this is the Lewis structure for methanol. Now let's come to multiple bonds. So if there are not enough electrons from the central atom for the central atom to attain an octet, so you end up getting a multiple bond. So in the step 5 process that we did not do, so if the central atom does not have an full octet, we change the lone pair of a surrounding atom into another bonding pair to the central atom, thus forming a multiple bond. So let's take an example of C2H4. So C2H4, you have carbon and carbon, and there are 4 hydrogens here. So now let's try and draw the bonds. So first things first, before we draw, let's write down the electrons. So there are 2 carbons, so 4 times 2 becomes 8 electrons, and you have 4 hydrogens, which becomes 1 times 4, which becomes 4. So you have 8 plus 4, a total of 12 electrons. So let's try drawing the bonds first. So 1, so 2 electrons, 4, 6, 8 and 10. Now notice that all the hydrogens are satisfied, but if you have, we have 10 electrons used, so we have 2 electrons left. These 2 electrons, for example, let's say if they go here, this becomes unbalanced. If it goes here, then this becomes unbalanced. So what do we do then? Is that rather than having an imbalance, we give both of them the bond and draw another bond. So we make that lone pair into another bond, creating the double bond. So this here is the Lewis structure for C2H4. So this is how you draw the Lewis structure for C2H4. Next, let's try another atom, which is nitrogen, N2. So nitrogen is a group 5 element, so it has 5 electrons. There are 2 nitrogens, so 5 times 2 is a total of 10 electrons. So we have nitrogen and nitrogen. So let's draw one single bond first. So when you draw one single bond, fine now. So we have 2 electrons gone, so there's 8 electrons left. Now if I put the electrons here, so 1, 2, 3 and then 4, notice that here there is an imbalance again, which means that here this is lacking 4 electrons. So what we can do now is that let's consider first that we are equally distributing the electrons among themselves. Even now they are not enough. So what do we do now here is that we convert one electron pair into a double bond. So what will happen now? Convert that into a double bond. Now even then it's not satisfied because this nitrogen only has 6 electrons. So what do we do now is that take another electron pair from another nitrogen and convert it into another bond, creating the final triple bond. So now notice that there are 6 electrons in the bond and two electrons in the lone pair, so which give 8 electrons each for each nitrogen here. So 2 electrons each for each nitrogen here. So resulting in the final formation of the N2 molecule. So next let's talk about resonance structure. So what is resonance here is that when you take an example of ozone, so ozone can be drawn in 2 methods. So this is one method and this is the second method. Notice that these are 2 different regional Lewis structures for the same molecule. So but neither structure depicts the O3 accurately. So what do we do here is that because in reality the oxygen-oxygen bonds are identical in length and energy. So because they are identical in length, it cannot be double bond here, it cannot be a single bond here. So what happens here is that the electrons themselves, so the structure of O3 here is shown more correctly using both Lewis structures. These are called as the resonance structures. So we use a 2-headed arrow to represent resonance. What we do here is we say that this electron pair comes here and this double bonded electron pair will go to the oxygen. So this motion or relative placement results in the resonance structures where both structures are valid at the same time, which means now you create a resonance hybrid where we combine two different structures to create a hybrid structure. So resonance here forms are not real bonding depictions. Basically the ozone does not change back and forth between its 2 resonance forms. The real structure is basically the average of its contributing resonance forms. So think about it like, when you have a blue horse and a red donkey, you get a purple mule. So the same way, a resonance hybrid is also a delocalized electron pair that can be accessed by both oxygen atoms. So when we represent Lewis structures, we depict electrons as localized either on one individual atom or between the bond between 2 atoms. But in a resonance hybrid, the electrons are delocalized. So remember that here, this is the important point to remember, that electrons are delocalized, which means that they do not stick to a certain atom or between a bond, but rather their density is spread over a few adjacent atoms. So here that bond is spread over both the atoms between the 3 oxygens. So this here is a representation of delocalized electrons. So we use dotted lines to represent the delocalized electrons. So one easier way of recognizing which structure has a which structures are having resonance is by calculating the bond order. So the resonance structures often generally end up with fractional bond orders because they do not have full bonding, they have partial bonding. So we have 3 electron pairs divided by 2 bonded atom pairs, which results in for a fractional bond order of 1.5. So which says that it is being distributed throughout the element. So let's try another atom of NO3 and let's try and see what would be the resonance structures for NO3. So NO3 here, again nitrogen is the least electronegative. So let's write oxygens and nitrogen in this manner first. So nitrogen is a group 5 element, so 5 electrons. Oxygen is a group 6 element, there are 3 of them, so it becomes 3 times 6, which is 18, and here 5. So 18 plus 5 here gives you 23. But notice that this is actually an ion, so NO3 minus, so which means that there is an extra electron here, so which is a total of 24 electrons. Now let's try and draw the electrons here. First let us write a bond, so 1, 2 and 3. So we have done the bonds now. Next write down the electrons for, so minus 6 electrons, which gives you a net of 18 electrons. So now we have 1, 2, 3 and you have 1, 2, 3 and you also have 1, 2 and 3. So which means 18 electrons are filled now, octet and everywhere. But notice that nitrogen is unbalanced because it does not have an octet. So what do we do here? We can take one electron pair, but this one electron pair can come from any one of these atoms. It can be from this oxygen, it can be from this oxygen, or it can be from this oxygen. Now all these 3 combined, each contributing atom's structure results in the resonance form. So for example, now let's say nitrogen If this is the oxygen that donates the electrons, so you have N double bond O, bond O, bond O. Or the other structure will be nitrogen, double bond O here, bond O, minus, or the other structure would be minus. So these are the three resonance structures for the structure for the atom here. So this is how we can know the actual resonance form. Now we have 4 shared electron pairs and 3 bonded atom pairs, so which gives you a fractional bond order of 1 1/3. So this would be the actual octet, because nitrogen here does not have a full octet, so it has to share. That sharing can come from any one of the oxygen atoms, resulting in these 3 resonance forms. So how do you differentiate a general structure from a resonance structure? Is by calculating the formal charge. So formal charge is basically the charge of an atom, the charge an atom would have if all the electrons were shared equally. So the formal charge of an atom is given by the formula number of valence electrons minus of the number of unshared valence electrons plus half of the number of shared electrons. For example, if you take oxygen here, for oxygen A, if you take oxygen A, here in the resonance form 1, the formal charge will be, there is a total of 6 electrons, 6 valence electrons for oxygen, minus of, there are 4 unshared electrons plus half of 4 shared electrons with the bond, which results in a 6 minus 4 minus 2, which gives you a charge of 0. Now when you calculate the same for other oxygens as well, you get 0, plus 1 and minus 1. And if you do the other resonance form, it becomes negative 1, plus 1 and 0. Now formal charges must always give you a sum to the actual charge of the species of all the resonance forms, which means that the sum of formal charges must be equal to the charge of the charge of the molecule. So for both these resonance structures, the formal charge will end up giving you a sum of 0. That's the reason why O3 here is a neutral molecule rather than being a charged molecule. Next comes the idea of how do you choose the resonance form and which would be the most important or the most stable resonance form. So the smaller the formal charges are always preferable to larger ones. And this next rule is that the same non-zero formal charges on adjacent atoms are not preferred. Avoid like charges on adjacent atoms. Next, you have a more negative formal charge should always reside on the more electronegative atom. Let's try and compare between these 3 possible resonance forms if I'm in CO minus. So when you look at the first one, so resonance form with always the least formal charges, the smaller formal charges is always preferred. So we eliminate the resonance structure 1. The second one is the negative charge should always be on the more electronegative atom. Here between nitrogen, carbon and oxygen, if there is a nitrogen here is the second most electronegative, so this is also not going to work. So here oxygen is the one that holds the negative charge and it is the one that has the highest electronegativity, so this one is the most preferred resonance form. Now oxygen formal charge and oxidation number are much different things. For a formal charge, the bonding electrons are called shared equally by the atom. The formal charge of any atom may change between the resonance forms, but for an oxidation number, the bonding electrons are transferred to a more the electronegative atom. So which means that the oxidation number of an atom is going to be same for all the resonance forms. So that's why never confuse formal charge and oxidation number. They are not the same. Now there are exceptions to this octet rule. One of them is in electron deficient atoms. These are atoms that are deficient in the number of electrons. For example, boron and beryllium are the most commonly electron deficient atoms. You have an odd electron species as well, where a molecule with an odd number of electrons is also called as a free radical. So these are other structures that can be exceptions to octet rule. There are also what we call expanded valence shells. For example, sulfur can take up to 12 electrons and phosphorus can take up to 10 electrons, resulting in expanded valence shells. Now these expanded valence shells are generally only possible for non-metals from period 3 or higher because of the presence of d orbitals. So that's the reason why you don't see it in group 1 or group 2, you only see it in period 2. So these are, for example, you can take examples of these. And for example, here you have SClF5, which results in this structure formation, which is an expanded valence shell. H3PO4 also has an expanded valence shell, so where it results in the formation of an expanded valence shell structure. You also have BFCl2, which is an electron deficient molecule. Next, let's talk about the main theory, the valence shell electron pair repulsion theory. Now each group of valence atoms around a central atom is always located as far as possible from others to minimize these repulsions. Remember that electrons repel themselves because they don't like charges always repel each other. So obviously when you have two electrons, they are always when you have two electron pairs that are closer together, they will always try to repel each other. Now a group of electrons in any number of electrons is any number of electrons that occupies a localized region around an atom. So this can be a single bond, this can be a double bond, a triple bond, a lone pair, or a single electron. All of these can be counted as a single group. So based on the way the electron repulsion works, we can classify the structure of molecules into 5 different shapes. The first one is a linear structure, the second one is a trigonal planar, the third one is a tetrahedral structure, the fourth one is a trigonal bipyramidal structure, and the last one is octahedral structure. Now the electron group arrangement is defined by both the bonding and the non-bonding electron groups. So the molecular shape here is always a 3-dimensional arrangement of nuclei joined together by the bonding groups. So this is defined only by the relative positions of the nuclei. So the molecular shape here is written by AXM-EN, where A represents the central atom, X represents the surrounding atom, E represents the number of valence electron groups, non-bonding valence electron groups, and M and N here are integers. Next example is the bond angle. So what is the bond angle? Bond angle is the angle formed by the nuclei with the two surrounding atoms with the nucleus of the central atom. So this angle here between the two adjacent nuclei is called as the bond angle. Now the angles in the figure generally show the difference between ideal and real bond angles. When you have a single bond, it results in an ideal bond angle. But when you have a double bond or the presence of different atoms, non-homogeneous atoms, generally result in the formation of a real bond angle, which is generally less than or greater than the ideal bond angle. But we do consider ideal bond angle to be a general basis. From that we can use methods to determine the actual bond angle. So let's start with the first structure, which is AX2, where you have one central atom and two adjacent atoms and no valence electron pairs. So this is no lone pairs. So you have A here in the center and two atoms on the edges. So this is the common structure for CS2, HCN and BEF2. Next you have AX3 arrangement. AX3 is where you have one central atom and 3 surrounding atoms. So this is a common structure called trigonal planar structure. So basically a triangular structure when you add all the structures. So this is the structure for SO3, BF3, NO3 minus and CO2 minus. This can also be a structure where we get another arrangement called AX2E, where E represents the electron pair. So if you have two surrounding atoms and one lone pair, that can also result in the same trigonal planar, but because of the presence of the lone pair, it rather looks bent like a V-shaped structure. So when you see this arrangement of one electron pair, one lone pair with two surrounding atoms, we can call that a V-shaped structure. Now, Let's talk about the factors that affect the bond angles. The first factor that affects the bond angle is the non-bonding or the lone pairs. So a lone pair reduces the bond angle between the structures because it can have more influence than a regular bonded electron pair, because bonded electron pairs are generally equally shared, but here non-bonded electron pairs have much more repulsion, resulting in a tighter bond angle between the adjacent atoms. Now a double bond will extend the bond angle, so will basically stretch the one side and compress the structure between the two adjacent structures. So resulting in a double bond will have a greater electron density than a single bond and repels the single bonds around being a bonded electron more than they repel each other. Next structure is AX4, where you have one single central atom and four surrounding atoms. That is a tetrahedral structure with a bond angle of 109.5. So I'm sorry, here in a trigonal planar the bond angle is 120 and in linear the bond angle is 180. Next, so in AX4 you can have two arrangements where you have one electron pair and two electron pairs. So when you have two electron pairs, you get a V-shaped structure. This is the common structure for H2O, OEF2 and SCl2. AX3E is the common structure, which is trigonal pyramidal structure, which is the common structure for NH3, PF3, ClO3- and H3O+. Tetrahedral structure is common for CH4, SiCl4, SO4 2- and ClO4-. So this is tetrahedral structure. Now, the next one is the 4-molecule arrangement, which is trigonal bipyramidal structure. So when you have a bipyramidal structure, you have two planes. One is the horizontal plane and the vertical plane. The horizontal plane is called as the equatorial part, and the vertical plane is the axial part. So the axial angle is 90 degrees and the equatorial angle is 120 degrees. So this is the common structure for AX5, where you have one central atom and 5 surrounding atoms. So this is the common structure for PF5, ASF5 and SOF2. You can also have AX4E, which is one lone pair, which is generally for SF4, XeO2F2, IF4 and IO2F2. You also have structures where you have two electron pairs, that is for ClF3 and BrF3, which is generally T-shaped. You have 3 electron pairs, then you end up with XeF2, I3 or IF2, where you end up with a linear structure. So the axial angle and the equatorial angle are important because these are two separate angles and the positions itself can change. Next, last one is AX6, where you have one central atom and 6 surrounding atoms. So this is an octahedral structure with an axial angle of 90 degrees and an equatorial angle also of 90 degrees. This is the common structure for SF6 and IOF-. You also have the same for BrF5, TEF- and XeF4- when you have one lone pair. And when you have two lone pairs, there is a common structure for XeF4- and ICl4-, where you end up getting an arrangement of AX4E2. Now, molecules in the period 2 or lesser cannot form more than 4 bonds. So the only structures that can form more than 4 bonds are the structures from periods 3 to 6. So this is the summary of what we did right now and regarding the structures and what arrangement we have. Now, how do you determine the 4 steps that are involved in converting the molecular formula into molecular shape? First, take the molecular formula and draw the Lewis structure. Once you have the Lewis structure, count all the electron groups that are surrounding the central atom. And third, once you have the electron group arrangement, note down the positions of any lone pairs and double bonds. Finally, 4, using that determine the bond angles. Finally, count the bonding and non-bonding electron groups separately and determine the molecular shape of AXM-EM. So let's start with PF3. Let's take an example of PF3. So first thing we need to do is to draw the Lewis structure. So we have PF3. Now draw the single bonds first. First things first, write down the number of valence electrons. So phosphorus is group 5. So 5. Fluorine, there are 3 of them. So group 7. So 5. 3 times 7, 21. You have 26 electrons. We have already used 6 electrons. So we have a total of 20 electrons left. So write down the atoms now. 1, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 now. 19, 20. So this is your Lewis structure. Now we have to write it in terms of AXMEN. So X is the number of surrounding atoms. There are 3 surrounding atoms. So AX3, and how many lone pairs on the central atom? There is one lone pair. So AX3E is the structure for PF3. So we can write PF3E. So PF3E, if you compare it to the structures that we have, so AX3E is the structure for trigonal pyramidal, and we can write here that this is trigonal pyramidal structure with a bond angle of less than 109.5 degrees because of the presence of the lone pair. So this lone pair can change the structure. So this is the ideal structure for trigonal pyramidal, PF3, which is going to be trigonal pyramidal structure. So try the same for COCl2 now. So COCl2, first draw the Lewis structure, then determine based on the number of valence electrons, so number of bonding atoms and the number of electron pairs, lone pairs on the central atom. So here the central atom will be the one that has, the central atom here is the carbon, the least electronegativity. So you end up with carbon in the center and oxygen surrounding it. Notice that because of the Lewis structure, you end up with a double bond. The double bond here is not going to be the same ideal angle. So there is no lone pairs on the carbon. So which means that there is AXE. There are 3 surrounding atoms, so AX3, and there is no electron pairs. E is 0. So the structure is AX3. The ideal structure for this is trigonal planar. But because there is a double bond, the angle will be less than 120 degrees, which is about 3 bonding groups, which gives you AX3 structure. So the same thing when you have more than necessary. So if you have 5 electrons, for example, you have SbF5, which is going to give you 5 fluorine atoms surrounding the lead. And this structure here now, you have AXE. So there is AX5, E0. So there is no electron pairs. So AX5 is trigonal bipyramidal. So we can write that structure here as trigonal bipyramidal. It's an ideal angle of 120 degrees equatorially and 90 degrees axially. So but bromine BrF5 has 42 valence electrons because there is an extra lone pair here, which means that this is going to be giving you, so you have a structure of AX5E1. So AX5E, if you look at the structures, the structure is square pyramidal, so which is the ideal structure, and because of the presence of that lone pair, the ideal bond angle will be less than 90 degrees. So with that we end the topic on molecular shapes. Next let's talk about the molecular shape and molecular polarity. So the overall molecular polarity generally depends on the shape and bond polarity. So the polarity of the molecule is generally determined by its dipole moment. So when do you call a molecule polar? It's only when one of the more bonds is polar bonds or the individual bond dipoles do not cancel each other. So what is a polar atom? A polar atom is where you have a partial bond where one of them is more electronegative than the other, and the more electronegative atom tries to attract the electrons towards itself. So let's take an example of CO2. See, if you take carbon here, which has an electronegativity of 2.5, and oxygen here, which has an electronegativity of 3.5, when you look at the carbon double bond, it generally looks polar, but notice that each of them will cancel each other when they go opposite sides. Because they cancel each other, CO2 is a linear and the bond angle is 180 degrees. So the individual bond polarities will cancel each other, resulting in no net dipole moment. Even though the bond itself is polar, but the net total of the net bond polarity is generally going to be cancelling each other, which results in zero angle formation. But that's not the case when you take H2O. H2O has a bond where you have both the dipole moments pointing upward, resulting in this structure where there is more positive on the bottom and there is more negative charge accumulating on the top, resulting in an overall molecular bond polarity where O is partially negative while the hydrogen atoms may be partially positive. So the same thing happens between two molecules here. For example, when you take CCl4, it's not polar because all the individual bond polarities will cancel each other. But CHCl3 is polar because of the presence of one hydrogen which changes its ability to have a polar structure. So try to predict the polarity of these following molecules now. So first draw the Lewis structure and then determine based on the electronegativity scale, determine whether they do have a polarity or not. When you take NH3, there is an overall bond polarity where hydrogen, where there is an electron structure which results in a molecular polarity towards nitrogen. So boron trifluoride is equally distributed, so there is not a big non-polar formation. So COS again, here the molecular bond polarity will always be there because it's not evenly distributed, resulting in a quite polar. Now, what is the effect of molecular polarity on behavior? So when you take two structures, when you take the cis and trans isomers are generally polar and trans isomers are non-polar. The main result here, because of C2H2Cl2 here, is that the trans structure will become non-polar because it cancels the polarity, but cis structure maintain its polarity. That's where the boiling point of the cis isomer is generally 13 degrees higher than that of the trans isomer, which can affect the polarity, the molecular bond polarity. So the difference in polarity can result in the difference in electronegativity can result in a bond polarity, and the bond polarity can result in molecular polarity. Molecular polarity can result in intermolecular forces. The intermolecular forces can affect physical properties, solubility, and the reactivity of an atom. So this is how we can think about the influence of the atomic properties on macroscopic behavior. Now, why do we need the shape of the molecules? Remember that most of your olfactory receptors are specifically shaped to accept the certain molecule, and only that molecule, if it enters there, only then will the olfactory sensor able to detect it. So that's how you can sense floral smells, camphor-like smells, and ethereal smells. So these molecules, so some molecules can have the same behavior even though they have a different shape. They can have an overall shape that's similar, where you see molecules like camphor, hexachloroethane, thiophosphoric dichloroethylamide, and cyclooctane, all of them with different molecules with the same chemical order. And another example of this molecular shape is enzyme action. So body's enzymes actually have a specific shape, and the molecule that enters must match that shape. If it doesn't match that shape, the molecule will not be able to undergo enzymatic reaction with the structure. So this is how the shape of the molecules can affect biological function in your body as well. So this is the idea behind enzymatic action and how molecular shape. So for example, most common way of curbing some diseases is to block a certain receptor which accepts a certain molecule with a molecule that's similar to that, resulting in the final non-functioning of that molecule. So which is most commonly called as an inhibitor. So which is a common class of pharmaceutical drugs that are used to treat many diseases. So this is how a molecular shape can have serious consequences towards the future and can result in really good pharmaceutical drugs as well. So with that, we end our lecture on shapes of molecules. I will see you again in the next lecture.